Hello, my name is Long Tran, and it's from Math 130, Numerical Analysis. This is the fall semester of 2022, Section 01. And my topic for my final project was higher order Taylor method. So what is it when it's used? So this uses the Taylor series to derive this method. It utilizes derivatives, of course. And it's another method to solve IVP problems. And this is used when a function has a derivative to derive from, and that is an IVP problem. So let's derive the higher order Taylor method. So let's consider the general form of IVP of y prime equals to f of t of y, and t is between a and b, and y of a is equal to some sort of alpha with a step size of h. So this is the general form of it, but we can expand it in the Taylor polynomial to get this. Yi plus 1 is equal to yi plus h y prime ti plus h squared over 2 y double prime ti, etc. So we can replace the y prime by the function, because the IVP problem really gives you a y prime equals to a function, and we can replace it. We can replace y double prime by the derivative of that function, and etc. So it's going to look something like yi plus 1 equals to yi plus hf ti yi plus h squared over 2 f prime ti yi, and etc. And this is generally the higher order Taylor method. But if we also consider Euler's method of OH, we can rewrite the higher order Taylor method using Euler's method, because we know that phi in Euler's method is just equal to f of ti yi. And so we can also rewrite it like this if we wanted to. And after everything, we can denote it to look like this. So what's some pros and cons to this method? Some pros is that it's a very straightforward method, as it is not so hard to do. As long as we have the derivative and we do the algebra correctly, we should be fine. Another thing is that we're able to perform error analysis. Due to the fact we're able to take derivatives, it will be a bit easier to do an error analysis using this method if possible. Some cons with this method is that the function could not have a derivative at all, as this method is based on derivatives, as we use the Taylor series to derive this method. Another con is that even if it has a lot of derivatives to compute, it's just going to get harder from there, and it could be impossible or very difficult to compute at all. And another thing is that other methods are more applicable in general to solve IVP problems, as taking derivatives could be a nuisance, and we can do other methods to find answer faster. And another thing is that it isn't always used in practice due to taking derivatives, as in real life most functions are either doesn't have a derivative or it's too difficult to derive derivative, so it's not always used in practice. So let's do an example. So let's do an IV problem using the order 2. And in this problem, we have y prime equals to y minus t squared plus 1 of y0 equals to 0.5. And t is between 0 and 2. And we have step size of 1. So as we already derived the method, it's going to look something like this. And we're going to use the order 2. So if it looks something like this, use the denotation of it, we can rewrite it one more time. And we're going to use w in this case for the next y value. So wi plus 1 is equals to wi plus h of the function of ti yi plus h over 2 f prime of ti yi. And when we use higher order Taylor method, when we take the derivative of the function, it is just taking the derivative of the function with respect to t plus the function with respect to y of the ti yi. So let's do a few iterations to see. So let's try to find W1. So to find W1, we're going to use the original information we have from the problem of W0. So W0 is equal to W0 plus HF of the function evaluated at T0 and Y0, which is already given in the IVP problem, plus H over 2 of the derivative of the function at T0, Y0. So we're just taking the partial derivative of this function with respect to t and respect to y, adding to each other at t0, y0. And so after we do that and plug everything in, we know that w1 is 2.5. To find w2, let's do a second iteration that we use the previous information of W1. To define W2 is actually just W1 plus 1, because it's I plus 1, is equal to W1 plus H of F, and it's the function evaluated at T1 and Y1 now, plus H over 2 of the derivative of the function at T1, Y1. And so after you do that, it's going to equal to this. And if you do one more iteration, we're going to use the previous information of W2 to find W3. And it's going to be W2 plus 1 is equal to W2 plus H of F of the function evaluated at T2 and Y2 plus H over 2 of the function of the derivative of the function evaluated at T2 plus Y2. And so if we do all that, W3 is equal to this. So in the end, Y doesn't matter. In general, this method, like I said, is very straightforward, and it's easier to use if possible. You're able to form error analysis better in this method because you're taking the derivatives. It is another method for solving IVP, so it's another method for you to use at your disposal if needed to solve IVPs. And like normal Taylor series, we can use this to understand asymptomatic behavior if the function does. In general, this method is more accurate, as it is a little bit more accurate than most other methods. And when doing research about when this method is used, we can use this method to find power flow analysis of electrical power systems. My references are that I went to office hours with Professor Mesa and lectures from Professor Mesa to learn about higher order Taylor method.